So I'm going to summarize the key concepts from the projectile motion lab at an angle. And we're going to solve one problem. This is complicated, but at the same time, it's the same VTAC stuff we've been learning about for 2 weeks now. The only complication is, the only thing we're going to add is we got to take our velocity vector, whatever the speed the object is launched at, and break it into components. Because some of the motion is going to be upward or downward, and some of it's going to be forward. That's the component stuff we learned with the vectors, the SOHCAHTOA. Once you understand that, then the equations for how we figure out problems, how far away, how high, how much time in the air, are the same thing we've been doing. So that's the good news. You just got to, it's just an extra layer. A second tutorial will attach, we'll look at ways we can take these equations and manipulate them to derive some kind of cool equations. They're not going to be tested, but I thought it'd be nice if you were aware of them because it allows us to do some predictions that otherwise would be difficult to do. So before we get to the results from the lab, which I'll do down here, the interpretation, and I'll show you a different type of graph. Let's look at this diagram here. This is really, really important conceptually. So you want to make sure you understand what I'm talking about here, and if you don't, you ask questions built on that. So we have some object that is launched with some launch velocity v, okay, at some angle theta. And what I want you to understand, I've already drawn them in, is that v launch can be broken into a vx and a vy component. Some of it's to the right or forward, some of it is upward. In fact, we can calculate that using SOHCAHTOA, that's going to be the launch speed times the cosine of that angle. And this is going to be the launch speed times the sine of that angle. So if you don't see that, you don't remember that from the vector stuff, work that out for yourself. Like for this one, I would say cosine is equal to adjacent, which is Vx, divided by hypotenuse, which is the launch speed. And then if I solve for the Vx, I get the equation I've already written there. Okay, so what we also want to understand is what happens to those components as the object rises. So notice the launch component, the launch velocities. What do you notice about their length of those arrows? And you notice that as it rises, they get smaller and smaller. And then as it falls, they start getting big, it gets bigger, at least from the top to the one that I have after that. So that is consistent with the idea that as it rises, it's going to slow down. As it falls, it's going to gain speed. But here we have to be really careful. It slows down and gains speeds in the vertical direction only because gravity is acting vertically on it. So that's the only thing that affects it. What I want you to know, even at the peak, it's still moving, just all horizontally. There's no vertical component. So the idea that it stops moving at the peak is half true. It stops moving vertically, but it's still moving forward. So think back to the rocket lab where you fired it straight up. It did come to a stop for a moment because there's no horizontal motion. All we've done between that and now is added the horizontal motion. So if I look at this and I take this second one and I break this into components, I would see there's a Vx and there's a Vy. And consistent with what I was saying is notice that the Vy component is shorter than the Vy component here. It's slowed down. Look at the Vx component. It's the same length as this one because it's still moving forward at a constant speed. Look at the Vx component here and the Vx component here, which is the speed is all Vx. Maybe I shouldn't put launch speed there. I'll just put Vx. It is equal to the launch. So the Vx doesn't change. That's consistent with horizontal projectile motion. If you fire something forward, it moves forward at a constant speed the entire time. So changing to an angle doesn't change that aspect at all. It just changes the vertical velocity part. That's no longer going to be initially zero. In horizontal projectile motion, we fired something like this, right? The initial velocity in the y direction was 0. Now it's equal to this. So that's the one adjustment we will have to make here more than anything. And then if on my way down, then we're moving down. There's my Vy. Notice it's in a negative direction. And here's our Vx. It's still the same as all the other ones. Notice the Vy here, well, actually, is if I just kind of look at the same height here, notice that this vector is bigger than this vector, meaning it's faster, but it's smaller than that vector that's slower, which is consistent with it being at an intermediate height. I didn't draw a vector at this spot here just before it hits the ground, but hopefully you can anticipate that that velocity vector, which is going to be tangent to the curve, So notice that all my velocity vectors, the launch velocity is tangent to that curve. But if I were to break that into components, it would still be moving forward Vx like the original, and the downward one, Vy, would be equal to this Vy, just in the opposite direction. So that symmetry is still there, and that can be useful. So, key ideas. What is the acceleration during the flight? In the horizontal direction, so we have ax and ay, it's 0. It's just like before. In the y direction, it is g, or I'll put a negative g there because that downward part is still valid. So let's now take the results from the lab. Two key things we wanted you to understand is how to angle change with range, and even I might even put a height in there. I'll actually draw it in a graph. So as angle increases, the range increases, but it doesn't continually increase. You saw it reach the peak, and hopefully you saw that peak was at 45 degrees, and some of you knew that prior. We have to prove that still, and I might be able to show you the proof in the next tutorial, but the lab should have shown that pretty clearly, especially if there's no drag effect. After 45 degrees, then the range starts to decrease again. So that implies something very important, not necessarily obvious. For a given range, there are two angles of approach. In other words, if I want to fire something that's 100 meters away, or if I want to hit something that's 100 meters away, and I can get there, so I have enough launch speed, then there's two angles that I can get. That's what the graph that you found. And I'm going to, so let me draw this graph here. Here is range. Here is theta, okay? And so what you found is you had something like this, where the peak was 45 degrees. And so what I'm talking about now is if I want to go, let's say this far, I can take a low angle and I can take a high angle. And so there's a relationship between those angles. They are complementary. So that can lead to a bunch of questions that if, let's say, I want to fire something a certain distance and I achieve that at 20 degrees, what other angle can get me there? 70 degrees as well. I could ask you what will go further, an object fired at a certain speed at 30 degrees versus 50 degrees. And there you have to think about it more. You ask yourself which one is closer to 45, because 45 is the max. 30 is 15 degrees from 45. 50 is 5 degrees away. So 50 degrees will go further than 35 or 30. And I'll illustrate that in a minute. Okay. The height and the time relationship between angle is more straightforward. So let me do a little graph, and I'm going to do this in multiple colors because it makes the thing stand out. If you can do, different pen or pencil colors, that's fine. If not, it's just a nice way of illustrating this idea here as well as height. So let's say I fire something I'm going to fire everything at a certain speed, and I'm going to look at how high it goes versus how far it goes. So this is a different graph than what I have up here. So make sure you understand the difference because it will look similar. So if I look at how high it goes, let's say I fire something at 20 degrees. So 20 degrees is fairly flat. So it's not going to go very high, and it's not going to go very far because it's far away from 45 degrees, relatively far away. So I'm just going to draw an arbitrary graph like this, okay? So let's say it goes that far. I'm going to label that 20 degrees. If I fire it instead at 70 degrees, okay, based on the rule here, we should anticipate going the same distance as 20, but it'll take a very different path. 70 is very vertical, so if I sketch 20s, 20's like this, 70 is like this, we expect it to go higher. So I'm going to have this go fairly high. And so I've got two paths that take me the same distance, just different approaches. Now these peaks should be directly over each other. I haven't done a great job with that, but that's important, okay? So the 70 will go higher. Now let's say I fire at 30. So if I fire at 30 degrees, we expect it to go higher than 20 degrees, not as high as 70. But since 30 degrees is also closer to 45, we expect it to go further. So 30 degrees will look like, excuse me, something like that. So the peak will be shifted over to the right. If I fire something at 60 to complement of 30, we'll go the same range as 30. We'll go lower than 70, higher than 30, so it'll look something like that. If I fire something at 40 degrees, it will go further than 30 because it's getting closer to 45. It'll go higher than 30, so it'll look something like that. And then if I fire something at 50 to complement a 40, it'll go the same distance, but a little bit higher. There's 50. So you get this interesting set of pairs. And if I want the maximum, I would go 45 which would look like that. But note that time in the air is, I don't want to say it's proportional to the sine of the angle. Okay, so the bigger the angle, the more time it's in the air. The height is also proportional to the sine of the angle. So the higher the angle, the higher the height. But the x, it turns out, that's a little bit more complicated. I'm not going to give a trig function here because it's probably not going to be helpful. Well, I'll put it, but don't really rely on it. It's sine of 2 theta, which is a subtle difference. So there's basically telling us there's two angles and gives the same range. Okay, so in the 5 minutes I have remaining, let's do a problem. Okay, so I'm going to change things around a little bit. I've got this big old VTAX table here, and I've added a final speed, and I've broken it up a little bit here, but it's pretty much the same thing. Here are all the equations that we should be aware of. I'm going to skip this part here. I'm not going to solve for the general ones because, you know what, I want you to do the VTAX problems to do this. So I'm going to go right down to example 3 right here and show how we would use the VTAX table to do that. So I'm told a football is kicked with a certain speed at a certain angle, and that's all you're told, and we can figure out how much time it's in the air, how far it went, and how high did it go. Then we can talk about what if we change it to 55 degrees, comparatively, how would it change? So I'm going to have to hustle here so I hopefully don't run out of time. So if I want to fill out my VTAX, it's the same thing. This is my initial speed. Okay, I called it launch speed on the front page. This is clearly my angle. So what do I know? I've got to differentiate horizontal from vertical. So what do I know about the initial speed? Well, in the horizontal direction, it's not 33, and in the vertical direction, it's not 33. I've got to find, so the initial speed in the x direction is my Vx, and Vx is V cos theta from above. Okay, so I'm not going to fill in the, let's see, how I'm going to do. I'm going to put the numbers down here. So if you do, yeah, we'll just do that later. All right, Vy is going to be V launch times the sine of the angle. So that's the one adjustment you have to make. Time in the air, we don't know. We don't know. How about the acceleration? Well, forward, it's 0. It's always 0. And here, it's negative 9.8. That's always going to be true. That hasn't changed. In terms of the change in position horizontally, that's what we're looking for. That's range. In terms of change in height, if we look at the whole flight, that's why I have split in half here, that's going to be 0. In other words, we're going to end up at the same height. But if we want to know for half the height, that's our maximum height, right? So for half the flight, that's your maximum height when you reach the peak. Okay, what do we know about VF? In the x direction, VF is simply going to be V cos theta. It's the same as our initial. It doesn't change. VY for the whole flight, or half the flight at the peak is 0. We know that. And for the whole flight, it's going to be the same as negative V sine theta. It's the opposite direction as the one up here. So we have quite a bit of information, just like we do for horizontal. So let's say I want to find time in the air. So if I go to the table here, I got to find where I know 3 pieces of information. I can say I got 1, 2, 3 pieces of information here, but that's not going to help me find time because it's just basically saying my initial and final, my speed is constant. So I've got to use this. So I know the initial, I know at the half the flight that it's 0, and I know the acceleration. Or I could use the full flight. So I'm going to take the easier of the two, and I'm going to do the solution right here. Okay, so if I know that, I know from this equations, I want to use this one right here. My final speed equals my initial speed plus acceleration times time. So I now take this information. My final speed, again, I'm going to do half the flight. So my final speed is 0. So let me write this. I'm going to do everything in y. Vy equals V naught y plus AT. Or I'm going to put minus GT. Minus because the acceleration is down, and GT. So what do I know about the final speed in the y direction at the peak? It's 0. What do I know about the initial speed? That's V launch sine of the angle minus G times T. So my time is equal to V sine theta, or negative V sine theta divided by negative G. Now this is just for half the flight. So if I want the full time in the air, I got to multiply that by 2 because the time it takes to go up equals the time it takes to come down. All right, I will continue this solution on the next tutorial because I'm running out of time here.